Welcome back to the demo on exercise 8. In this exercise, you will add a driving torque and a torque to limit the motion of a joint to the 4-bar mechanism you built in the previous chapters. You'll also compare the results of a kinematic simulation to a dynamic simulation to help illustrate their differences. You can either use the model from the previous exercise or you can open the file called Chapter 8 Exercise Start in the Chapter 8 folder. So I'll go to File, Open, Model. In Chapter 8 folder, I'll be selecting Chapter 8 Exercise Start. So this is the same point wherein we had stopped in the previous exercise. So now, first let's go ahead and deactivate the motion that we had created in the previous exercise, which is motion 1. So let's deactivate this motion. So right click on this and say deactivate. Now next let's go to joint 0, which is this particular joint, and we had given some initial condition for this joint 0, which is the velocity. So let's uncheck that to remove the initial condition on this joint. Now let's create a driving force. So right click on the client specific toolbar. So let me give some meaningful name to it, called the driving torque. Okay. So here I will set the force option to action reaction, and then in the properties I'll go to the drop down menu and select rotational. So click on body 1 and I will select body 1 here. For action force on, I'll be selecting body 1, and for the reaction force on the body 2, I will keep it as the ground body. So the force I want it to be applied at point F, so at this particular location. And the local reference frame, I want it to be same as the global reference frame. So I just keep it as it is. Now I'll be going to the rotational properties. So here I'll enter a linear value for the torque in the y direction as 150 Newton mm. So I've applied the torque in the y direction. So let me now save this model. As 4-bar torque. Okay, so now let's run this analysis. So Motionsolve is running in the background and the simulation is complete. So let's invoke HyperView, click on Animate, and HyperView is on the right hand side here. Click on the play button. Okay, it's too fast. Let's decrease its speed. So here we can see that we can decrease the speed. We can see that the small bar, it completes one full rotation. Okay, so this is what we observe. And it's rotating very fast because we've given it a driving torque of 150 Newton mm. So that's the reason it's rotating at a very fast speed. Okay, it's this particular small bar that you can see, it's completing one full rotation. Now pause this animation and go back to your Motionview window. Now let's create a BYOP function to limit the motion. So right click on the forces and call it BYOP torque. Click OK. So here you can go to action reaction for the force option, and here in the properties select rotational, and for body 1 you can select free body, and for body 2 it's ground body, and for point 1 you can select point A, so which is at this point. So we are applying the by-stop torque at this particular location. And the local reference frame, I want it to be same as the global reference frame, so I keep it as it is. Now let's go to the rotation properties. So here you change the selection from linear to expression. So, and you go to the expression builder, and now you'll start creating the by-stop function. So the by-stop function is found in the general tab. Click on by-stop, and please make sure that you use the backquotes, the right backquotes, to create this expression. It's going to be a really long expression, so make sure you watch it carefully. So first, we need to go to the motion tab. So after adding the by-stop function, let's go to the motion tab to find the AZ function. So here is the AZ function. So we add that. Okay. So once this is done, we go to the properties tab. So in the properties tab, we'll expand the joints option, and under joints option, let's expand the joint 0 and scroll down. So expand the marker i's id string and say add. Okay, so you got that. So the AZ function or the AZ function will measure the Z angular displacement of joint 0, which is basically the first argument needed for the by-stop function. Okay, so now let's close this particular, let's delete that closing bracket, closing parenthesis, because the expression has to still go on. Now you can leave a comma and come to the next. You can come to the place which is after 1 comma, and here let's select the ID string of the J marker. Okay, so you minimize this, you expand marker J and select its ID string and say add. Okay, so this gets done. So once this is done, here you can go ahead and put this in the curly braces. Okay, so this should be in the curly braces and it should be closed with this close parenthesis. Now you can go to the next comma. So the second term in the by-stop function is the derivative of the first term. Okay, so you need to go to the motion tab again and select the WZ function, which is this. So you need to do the same thing what you did before. Okay, select the ID string of the I marker and then the J marker of joint 0. So go to properties, go to expand joints, expand joint 0, expand marker I, and then select its ID string, say add. Okay, this gets added. Now go out of this, put open and close the curly braces. Now come here, minimize this, maximize the marker J and select its ID string, which is here. Say add. So this is done. So the WZ function will measure the Z angular velocity of the joint 0 with respect to the ground, which is the second argument needed for the by-stop function. Now you can move to the next comma. So once this is done, the third argument is basically the lower bound of the independent variable, and the fourth argument will be the upper bound of the independent variable. So for that, I'll be choosing minus 10 into pi by 180. Sorry. So minus 10 into pi by 180. That's the lower bound. So I'm doing pi by 180 because the lower bound of the allowable deflection, it has to have the resisting torque that has to be entered in radians. So to convert into radians, I'm multiplying it by pi and then dividing it by 180. So 10 into pi by 180, that's the lower bound. The upper bound will be positive 10 into pi by 180. Okay. So all these should be separated by commas. So we've entered the lower and the upper bound. So the fifth argument for the bi-stop is the stiffness value, right? So you can enter 1e to the power 4, and the sixth argument will be the deformation characteristic. So you can add 2 there. So these are some of the values that are entered out of experience. So once you've once you've run the simulation and you've faced a failure, so it basically comes by experience. So these values, okay. So first you can try to use some nominal values, and then after you get experienced, you can try using the exact values. So after entering the deformation characteristic, the last thing is to enter. So 100 is the maximum damping coefficient, and the last thing that we'll have to enter is the penetration. So that's 0.1. Okay, you see this expression is too huge. It's very easy to make mistakes here, but if you do it carefully, then we can enter the expression without any mistakes. So let's see if there are any mistakes in the expression. You can check that by clicking on this evaluated option. Okay, so this shows that there are no mistakes in this expression. Say OK, and it gets populated in the expression tab. So now you can save this model as 4-bar bi-stop. Then click on save, and now you can run the model. Okay, the analysis is complete. So let's go to animate and bring up HyperView. Okay, so click on the play button. So you should notice that the driving torque, it moves the mechanism until it hits the limit of the bi-stop torque. So we've defined positive 10 into pi by 180 as the upper bound and the lower bound as negative 10 into pi by 180. So this causes the bounce back motion of this particular mechanism. Okay, so you can pause this. Let's go back to Motionview. Now let's create an output measure for the bi-stop function. So for this, click on the output option in the client specific toolbar. Let's call this bi-stop torque output. Okay, and then say OK. So here let's go to the drop down menu and select expressions. Let's go to the F2 field to activate it. Go to the expression builder. Now let's create a V-torque function to measure the bi-stop torque. Okay, so this V-torque is found in the force tab. So select the V-torque function. Now you can go to the properties. Under properties you can go to the forces. Expand the forces. You have the bi-stop torque. You can expand that and take its ID string. Say add. The next argument for this is the J flag, which means the forces or the moments are reported either for I or J. So I will be entering 070, which means I want the bi-stop torque reported for the I marker, and 7 represents the torque component along the y-axis, And the last one, 0 value here represents the reference marker is along the global reference frame. Okay, so you can click on evaluate it to check if your expression is right, and then click on OK. So now you can run the analysis again. The analysis is complete. So let's go ahead and plot the torque output. Okay, so go to the plot option, and this brings up HyperGraph. So here in the Y type, we'll go to the expressions, and then the Y request, we select the by stop torque output, and in the Y component, we select F2 and hit on apply. So this is what you're supposed to see. This is the x-axis, which is the time from 0 to 5 seconds, and this is your torque value. So the bouncing effect what we saw in the animation is recorded in terms of this particular curve in HyperGraph. Okay, you can stop this. You can now go back to your Motionview graphical user interface. Now let's compare this dynamic simulation with a kinematic variant of the same model. Okay, so now let's go back and let's go back and deactivate this particular driving torque. Okay, so we go to the torque option in the forces. Okay, so we go to the driving torque first, this particular driving torque, and we deactivate it. So right click on this driving torque and say deactivate, and then you right click on the motion, basically right click on the motion 1 and then click activate. So now this recreates a kinematic system for our model. So previously it was a dynamic system, but now what you did is you deactivated this driving torque and you activated this motion. So this removes another degree of freedom, so thus making the total degree of freedom of this entire system 0. Right? You can check that. You can go to tools, check model, degree of freedom. You can see that the total degree of freedom for this entire system is now 0. So thus now you'll be running a kinematic simulation. So once this is done, run the analysis. So go to the run panel, save your model as 4-bar by stop motion, and run the analysis. Okay, so the analysis is complete. Let's animate. So now you can see that even though the by-stop torque has been applied, the small bar, it completes a complete revolution. So notice that the joint with this motion, it keeps moving the mechanism regardless of this by-stop torque that we have applied here. So this is how kinematic models behave. That is, the motion driving the mechanism must be followed. Okay. So what I'm trying to say is, when it is a dynamic model, the by-stop torque that we had applied on this end, it had an effect on the entire system, wherein we had the bounce back effect and the animation was completely different. But in this case, even though we have the by-stop torque, but since it is a kinematic simulation, that effect of the by-stop torque is completely disregarded. Okay. So I hope now you understand the difference between the kinematic simulation and the dynamic simulation. So now you can stop the animation. Go back to your motion view window, and you can finally save this file as, just want to save the model, so you can save this model as 4-bar by stop. Okay, so this brings you to the end of exercise 8. Thank you.